Okay, let's start. Okay, well, it's really an honor for the UV Club that we have the PI of the next big UV mission giving a talk to us, a sneak preview of a mission which should see flight in a couple of years. We'll know more by the end of this talk. The speaker today is Ellie Waxman. He's a professor of physics and astronomy or astrophysics at the Waxman Institute of Sciences in Israel. Ellie is a highly respected theorist who is known for undertaking incisive work across astronomy. His thesis work was on shocks, in fact, on a problem classical to the field of nuclear explosions, self-similar solutions to strong explosions, which some of you may remember the more classic name would have been set out Taylor explosions, but Ellie went obviously beyond that. Fortunately, his thesis work had prepared him very well because a few years later, literally, afterglows from gamma ray bursts were discovered, and Ellie was in a fantastic position to write a dozen seminal papers on many, many aspects of gamma ray bursts. And that's where during that period, I met Ellie. Ellie's next foray was on the then nascent and perhaps in questionable field of high energy neutrinos. Of course, this is now a well-established field with regular detection from IceCube. Nonetheless, the early work that he did with John Bacall makes him, a towering figure in this field. And the Waxman-Bacall limit is a cornerstone of the field known to everyone who uses IceCube data. With the discoveries of X-ray shock breakout from supernova 20,008D, in fact, by our own Alicia Soderberg, Ellie wrote a number of fundamental papers on shock breakout, emphasizing what appears nuisance complications, but which matter tremendously, such as Comptonization, to the final observations of these shock breakout. Of late, he has focused on fast radio bursts, cosmic rays, very high energy cosmic rays, cluster shocks, neutron star coalescence. Most scientists who are very well known, who get professorships or distinction, actually, if you look at it, in the end, it turns out they're pretty good at one thing. So you're a theorist, you're good at theory. An observer, you're good at observer. You may write a few somewhat related papers. But then there's an order of magnitude decrease, maybe a factor of 20 decrease. If you ask how many, maybe two orders, how many actually are good at two things? Meaning, you actually do two distinct things like observations and theory, or theory and experiment. Well, then it's pretty small. And then you say how many there are who do three things. So that's another two orders of magnitude. And I know only a few in that last category. Ellie is pretty amazing because he started off as a heavy-duty theorist working on obscure problems such as strong shock breakouts, but then obviously very cleverly applied to across astronomy. But more or less, I would say he is the founder of the modern astrophysical program at Weizmann, took it away from sort of a largely theory-oriented program to a very strong observational and now experimental program in astronomy. And he was able to switch from being a theorist to being a PI of a mission, which requires different skills. It requires you to schmooze with ministers and hobnob with engineers, do hard engineering calculations while not losing of the astrophysical aims of the mission, and just grungy details that take a long, long time, which is why, we all admire PIs of successful projects. Anyway, so let me just end by saying I first met Ellie, I would say maybe 97 at Institute for Advanced Study. Peter Goldreich introduced, you should get to know Ellie. And he said something, as usual, very kind words, with some humor. He said, he's just an SOB like you, but he's also very bright. Anyway, okay. So I hope this doesn't translate to very bad, these days sense of humor is pretty much an art of lost art, but at least with the Israelis, I can make such jokes. Okay, well, Eli, welcome.
Shri, thank you for this surprising, very warm introduction. Just for this, it was worth preparing the talk. Thank you everyone for waking up early or late for this talk, and thanks for the opportunity to present ULTRASAT to this group. Actually, I think quite a few of the group know ULTRASAT very well. There were partners at different parts of the way. So I'm happy to see you all here. And I'll tell you about the project as it is today. I will say some words about the scientific goals, but I will also devote a significant part of the time to the implementation, which I believe is also of interest to you, as Ilaria wrote me. And there will be another talk, I think, much more detailed by Rolf, who is also present here, about the camera, right, next week. So, or I don't remember the exact date. So we'll hear more about the details of the detector. Okay, and of course you are welcome to stop me and ask questions as we go along. Let me share my presentation. Okay, so do you see the slide okay, Ilaria?
Yes.
Okay, so let's start. So ULTRASAT is a spacecraft that will carry a wide field UV telescope to a geostationary orbit, and it will enable us to revolutionize our ability to study transient objects in the universe. The funding partners of the mission are the Israeli Space Agency, the Waxman Institute, DESI, some members of DESI are here, Rolf, Merlin, Shri, and NASA. And our industry partners are the Israeli Aerospace Industries, ELOP, and Tower. I will say a few words about these companies as we go along. Excuse me for a second, the lights turn off here automatically. Yes, so the mission is managed by a program office at Weizmann Institute. We have a very experienced program manager, Udi Netzer, and there's a group of scientists here that I'm sure you know who are all involved in the mission: Avishai Galyam, Eran Ofek, Sagi Ben-Ami, Yossi Schwarzwald. And we have a strong collaboration with DESI. The DESI PI of the camera is David Berge, and Merlin and Rolf are leading the construction of the camera are here with us, and Marek Kowalski is another member of the DESI team. So the goal of ULTRASAT is to study transient phenomena. And the reason that this is an exciting frontier at the moment is twofold. First, there are very interesting open questions. So some of the objects that we are going to study are collisions and mergers of stars, neutron stars, and neutron-star black hole mergers, supernovae explosions, and tidal disruption events. We, of course, are interested in understanding these events, the astrophysics of these events, but all of them are related to some more fundamental open questions in astrophysics, like the origin of the heavy elements beyond the iron, which are probably related to mergers involving neutron stars. We will will be able to measure the expansion rate, the current Hubble constant, independent of other measurements. We don't understand how stars explode, and this is still an open question in astrophysics for many decades. Studying tidal reception events will enable us to study the demographics of black holes at the centers of galaxies, to study how these black holes affect the stellar clusters around them, and so on. The second reason is that technology now enables the construction of telescopes with very wide field of view. Of course, if you want to study transient events and you have a very narrow field of view, it is impossible to carry out a systematic study because the probability that you will be pointing in the right time, in the right place is very small. And if you want to do a systematic study of transient events, you need wide field instruments. And there are such wide field observatories across the spectrum which are being constructed. This is a partial list of them, both in the optical and also in the X-rays and gamma rays in space, and the very high energy gamma rays also on the ground, gravitational wave detectors, high energy neutrino detectors. And surprisingly, the UV band is missing from this wide range effort of wide field observatories, and ULTRASAT will correct this situation. So the unique properties of the ULTRASAT telescope are a very large field of view, about 200 square degrees, with high UV sensitivity, 22.4 magnitude for 900-second exposure at 5 sigma. And looking at the UV has several advantages. There's a very low sky background. We are looking for hot sources, so we expect strong signals in the UV. And of course, you have to be in space in order to detect the UV signal. So if you look at the plot that is here on the right-hand side, you see the volume accessible to different observatories as a function of wavelength. This is ULTRASAT is normalized here to 10. This Aronofsky made the plot. I don't know why he chose 10, but this is how he made it. So this is the volume accessible to different instruments. ULTRASAT is 10 here. You can compare it to GALEX. It is about 300 times more sensitive than GALEX. You can compare it to existing facilities on the ground. Some of them are under construction. You see that ULTRASAT is 2 orders of magnitude more sensitive. And you can compare it to LSST that should start operating at 2024. Okay, so this is a ground-based optical observatory. And although it is a much bigger telescope, because we are in space and observing in the UV, we achieve a similar sensitivity to transients with a much smaller instrument. So in addition to the very large volume, we will provide UV information, which is unique and can be done only from space. We will have a continuous cadence. We will be observing objects over months with a minute cadence. This is impossible to do from the ground. And since we will be in a geo orbit, we will transmit alerts on new events on timescales of minutes to the entire astrophysical community that will be able to follow up the events that we will be identifying. This is a list of source types and science goals that ULTRASAT will address. I will not go through the list. I just want to emphasize that with this wide field sensitive UV instrument that will enable monitoring of far larger number of sources compared to anything that is possible today, we expect to make significant progress on many open questions. I've already mentioned stellar mergers and supernovae explosions, but we would, for example, have continuous light curves for many thousands of AGNs, and we can do interesting AGN physics with this. We'll have a lot of information of variable stars, and there's also, of course, room for serendipitous discoveries. So I believe that ULTRASAT would have a wide impact on many subfields of astronomy. I would talk in some more detail about two of our science goals, of the primary science goals. So one of our key science goals is emerging binary neutron stars. As you know, tight binaries can merge on a Hubble timescale if they are tight enough, a few million kilometers. And gravitational waves that these events emit were a fundamental prediction of GR. And the detection in 2016 was a major success of GR and of the LIGO experiment. It led to the Nobel Prize in 2017. The first detection was, as you know, of a binary black hole system of two 30 solar mass binaries. We will be after events involving neutron stars as one of the binary merging. In a merger of neutron star binary or neutron black hole binary, we expect some of the neutron star material to be torn away and ejected at nearly the speed of light away from the sources. And due to the high neutron contact of these objects, we expect the production of so-called rapid neutron capture process elements, which are part of those heavy elements beyond iron, the origin of which we do not know. So the detection of the electromagnetic emission following the gravitational wave signal is and will be one of the major goals of transit astronomy in the coming decade. We would like to identify the origin of the heavy elements. Measuring the electromagnetic properties would enable us to constrain the properties of the ejected material and therefore to constrain the properties of the neutron stars, so that properties of matter at nuclear densities. Accurate localization of the mergers that require electromagnetic detection will help us to identify the host galaxies and therefore both to measure the current value of H naught and also to constrain the progenitor systems by identifying the exact environment in which the merger took place. With the upgrades of LIGO, we expect somewhere around the beginning of 25 to have some 10 detections of neutron star merger events per year out to a distance of about 300 megaparsecs with an angular uncertainty of about 100 square degrees. ULTRASAT would have a unique, would have several unique advantages in trying to detect the following electromagnetic signal. It would have, being in space, instantaneous access to more than 50% of the sky, and we will reach any point in the sky in a few minutes' time. The very wide field of view implies that we will cover the entire GWR box in a single image. And our UV sensitivity is such that, based on current estimates of the UV emission, we should be sensitive to events beyond the LIGO horizon. I should note that detections in other bands, like in the X-rays and radios, are going to be very challenging. Significant X-ray emission is expected only on a small fraction of the events, presumably by jets that are beamed directly towards us. And radio detection is going to be quite late. The radio signal is going to be faint and rising over very long times. So it will be difficult to detect, and it would enable us detection only at very late times. The timeline for our mission is actually set by the gravitational wave detector upgrade timeline. We want to be in space by 2025 to be ready for this enhanced rate of neutron star merger detections. The event, the single so far, the neutron star merger event that was identified electromagnetically provides a very strong support to this ULTRASAT mission in the context of gravitational wave follow-ups. As you know, this was a very nearby event at the distance of 40 megaparsecs, a very fortuitous event for us. The light that was emitted from this event was detected about half a day after the GW signal, and it was very bright in the UV. The electromagnetic signal was detected by searching over the galaxies which were contained in the GW error box, and this is something that's going to be extremely difficult for events that would be detected at 300 megaparsecs because there would be thousands of galaxies in the error box. And also the X-ray and gamma ray signal, as expected, were quite weak, so they would not be detectable at distances beyond 60 megaparsec. And the infrared and radio, again, as expected, at large distances would only enable detection at very late times and would be very challenging. The detection of the electromagnetic emission in this case proved that indeed heavy elements, radioactive elements are produced in the explosion, but how heavy is unclear. And one of the things that we learned is that early UV detections would be very useful in discriminating different models for the ejecta and different suggestions for the composition of the ejecta. So all this is a very strong support for the idea of trying to do GW follow-ups using electromagnetic, using UV wide field observations in space. Another key science goal is the supernova explosions. As you know, the supernova mechanism is still under debate and not well understood. And one of the ways to make progress is to identify the initial conditions of the explosion, or in other words, to determine which star exposes which type of supernovae. Currently, we have a handful of examples where the progenitor star was identified in a pre-explosion high-resolution image of a nearby galaxy where a supernova was later detected. You see some example here on the slide, but there are only a handful of examples, and the sample is not going to increase very much or very rapidly. And an alternative to the identification of the progenitor star is an early detection in the UV. The early emission from the exploding star contains information that is erased afterwards as the star expands. And an early detection, including the UV, would enable us to determine the progenitor type, the size, the composition of the envelope, to constrain the explosion properties, and also to constrain the pre-explosion evolution by the detection of emission from possible circumstellar medium surrounding the exploding star. On the right hand side, the top plot, you can see an example, two examples of detections that we have. You see that the UV observations that we had from GALEX provide data with very large error bars. So the detections that we have so far serve us to sort of verify that our models are reasonable and that they enable us to make the correct predictions about what we will detect with a much better instrument. And what you see in the bottom plot is a simulated data for a supernova explosion as it would be detected by ULTRASAT from space, and with an additional ground-based detection with a much lower cadence. And as an example, you see in the insert the accuracy with which the radius and explosion velocity would be determined by these observations. So we would be able to to determine both parameters to an accuracy of about 10%, which is an order of magnitude better than is possible today. On the left plot, the histogram, you see the expected number of supernova detections at an age earlier than 1 day by ULTRASAT and by other observatories. And you see that ULTRASAT will detect hundreds of these events per year. And the importance of detecting a large number of events is that it would enable us to detect the rarer types, the blue supergiant and Wolf Rayet type explosions, and constrain the properties of their progenitors. So one of the key goals is to identify the progenitors of a wide range of supernova explosions. And if you do not have a large detection rate, you just miss all these rare type of events. The insert of the histogram, you see the number of events that will be detected by ULTRASAT at an age earlier than 1 hour. So you see we'll have even tens of events like this, while other facilities will not detect any event at such a short time scale. And this will provide information about the shock breakout that Sri mentioned, and would give us key information about the progenitor stars. I would mention one more science goal, which is not of the high energy astrophysics type, which is related to planet habitability. As you know, terrestrial planets in the habitable zone, so-called, are searched for under M dwarfs and young solar analogs. And these stars apparently are quite UV active. And strong UV flares can do several things. First, they may severely limit habitability. On the other hand, they may allow some prebiotic chemistry. And they may also complicate the analysis because they may produce ozone due to the photodissociation of water and carbon dioxide in the atmosphere of those planets. And we may confuse the detection of this ozone with ozone due to biological activities. So the UV flares are important for understanding these issues. And the flare rates and the flare luminosity distributions are very poorly known today. And ULTRASAT will change the situation. We will monitor nearly 1 million of stars, and we will be able to determine the new UV flare frequency, luminosity distribution, and also to determine the dependence of these properties on the properties of the stars, like the spectral type and rotation period and so on. And this one thing that this will enable is to determine which type of stars are more likely to host habitable planets. And this may be very useful for directing expensive spectroscopic searches for biomarkers in planets around the nearby M dwarfs that would be detected. Okay, so that's it about the very brief description of some of our key science goals. And let us now go to some description of the implementation. So at the center of the mission is the telescope that you see in the middle plot. The top part of the telescope is a very long baffle that is intended to stop both stray light, but also high energy electrons that would produce Cherenkov emission. I will say a few words about this later. The bottom part is the telescope itself. The telescope is being built by ELOP, which is an Israeli industry that builds space telescopes. And it is based on the design that was carried out here at Waxman. At the center of the telescope sits the UV camera I will say a few words about it as well. The camera is the contribution of our DAISY collaborators from Berlin. They are building the camera. The sensor, the UV sensor that I would also mention briefly, is being produced by Tower, which is an Israeli company, and it is the chips are being purchased by DAISY that would be constructing the complete camera. And the first batch of chips is already in Germany. I'll say something about that later on. The spacecraft is being built by the Israeli Aerospace Industries, which builds the Israeli satellites. You see the telescope sitting on top of the body of the satellite, which is mainly an engine with a big fuel tank. The satellite is going to be launched by NASA. This is NASA's contribution into a geotransfer orbit. We were hoping for a geo orbit, which would make the satellite much smaller and lighter. But since we got the launch to geotransfer orbit, which implies that we need to circularize our orbit, we had to add an engine and a large fuel tank. This is why the satellite looks as it is. So the dimensions of the satellite are 1 by 1 by 3 meters approximately. The mass is 900 kilograms, 500 of which is the propellant. The launch is planned for the end of 2024, and the mission is guaranteed for, in terms of reliability, for at least 3 years in position in space. A word about the mission profile before we go a little bit more into the details of the construction. We will carry out an all-sky survey for about 3 hours a day during the first 6 months of the mission. And this would produce a significantly deeper map than Galax produced. This is interesting in itself, but it is crucial for us also for having a reference image for every point on the sky for the detection of new transient events that appear. Most of the time, we would be just staring at the same field. We will be staring near the north and south ecliptic poles in the summer and winter. This is to both minimize the zodiacal light background, which is our dominant background, and to minimize the galactic extinction. We will be transmitting the data to the ground continuously, and we'll have alerts on new events distributed to the entire community within less than 15 minutes. We will have a target of opportunity program, for example, for following the gravitational wave alerts. As I mentioned, we will have instantaneous access to more than 50% of the sky, reaching any point in less than 15 minutes and being able to stay there regardless of the position of the sun and the communication for more than 3 hours. There is no limit to the TOO numbers essentially, except for TOOs in which we are in negative power balance. This is an unfavorable angle to the sun. But this is expected to happen only for 15% of the sky. So essentially, we are unlimited in the ability to carry out your observations. So a bit more about the spacecraft and the telescope. This is a blow-up of the telescope. You can be impressed that the engineers at IAI are really working and they are producing nice plots. I think I would not go into the details of this figure, just to reiterate that we have the telescope sitting on top of the satellite body. We have this large buffel going up, and we have a cover that will be probably only used up to the reaching the sky location, and then we would turn it permanently open. You see on the bottom the engine, you see the APM, this is the antenna, the two antennas. You can see the solar panel, and you can see the radiators. These are the darker blue things. The satellite is, we're going to use only passive cooling, so we have relatively large radiators here. Okay, if you have questions about the satellite, I will be happy to answer later. Okay, let's talk about the telescope and the camera. We plan to work in the 220 and 280 nanometer band, and in order to reach this volume that I've described for detecting transients, we require sensitivity of 1.5 times 10⁻³ photons per square centimeter per second for 900 second integration at 5 sigma. This is the 22.4 magnitudes, and we require the sensitivity over a fairly large field of view of 170 square degrees. This translates to strict requirements on the optics, on the detector, and the buffer. The key requirements are the field of view, the point spread function, which we require to be less than 15 arcsecond, and the out-of-band suppression, which we require to be significantly less than 1%. For the detector, we need a high quantum efficiency in the UV, which we set to be above 70%. I will get into that. And in order to minimize the background, we need to have a very low dark current, less than 0.03 electrons per second. And for this reason, we cool the detector to about 200 Kelvin. This is the sort of the minimal temperature we can reach using passive cooling only. And we require very low read noise, less than 3 electrons per pixel. And we also have stringent requirements on the buffer. We need to suppress the stray light by about 11 orders of magnitude. And the buffer also needs to suppress the flux of cosmic ray electrons that would hit the optics. The high energy electrons that are confined in the magnetic belts in geo orbit, when they pass through the optics, they produce Cherenkov light. And this Cherenkov light is blue, and this produces a large background in the UV. And so the buffer is also heavy. It has a significant column density in order to suppress the flux of electrons that hit the optics. This is something that is sort of unique to geo and to UV. If you work in the optical, this is not so important. This is the design of the telescope. You see the big buffer on the right-hand side. It's a Schmidt design. The light enters a double corrector. It is being reflected from a mirror into a field flattener lens, and then it hits the detector. The aperture is 33 centimeters. The mirror is 50 centimeters. Both the corrector and the field flattener are a double lens made of one from fused silica and the other from calcium fluoride, in order to correct for the aberrations. We have added, after our initial design, a filter that I would say a few words about that would enable us to suppress the out-of-band, the red leak, to less than 1%. We were originally hoping to achieve these values by coatings on the optics, but this seems to be too challenging, so we had to add a filter. And we also added a focus mechanism, so the field flattener double lens would be mounted on a focus mechanism. This is in order to address the very low depth of our focus, which I will mention in a second. Some of the guidelines or considerations that dictated this design. So working in the UV, you have a limited set of materials that you can work with that have high transparency. And so we are using calcium fluoride infused silica and sapphire for the filter. The challenge is that the refraction index changes rapidly at short wavelengths, so it's difficult to correct for aberrations on a wide field of view. We use the calcium fluoride and fused silica in tandem because they have different behavior, so that this enables us to minimize the aberrations. What else should I say? I mentioned that we added a filter in order to achieve our out-of-band suppression. I will not say too much about the filter. So it's 1,000 layers of different hafnium oxide layers. I will show you a graph about the measured properties of the filter shortly. Some design issues that one needs to consider. Because of this very wide field of view, we have a short focal depth, which is less than 20 microns, and this requires both high stability of the telescope, and we concluded a focus mechanism. We will be maintaining the telescope at 300 degrees Kelvin in order to enable us to test the optics on ground. Second again, turn on the light again. But the gradients that we will have in space would not enable us to determine the exact correct position of the focal plane to the required accuracy, just doing the thermal analysis. So we had to add a focus mechanism. And another point which is crucial to remember is that contamination is a major issue in the UV. The organic materials that are being used for glues and such constructive elements, they emit all sorts of organic materials when they're in space, and this would be accumulated on the detector, which is the coldest part of the system. As I mentioned, it would be at 200 Kelvin and the rest at 300 Kelvin. And these contaminants have high absorption in the UV. So very special care needs to be taken with choosing the materials and also with the construction plan in order to avoid contamination. And we will also have the ability to heat up the detector and the telescope periodically to get rid of accumulated contamination while we are in space. This is just to show that the project is reality. The first calcium fluoride blank was already produced by Helma and is being polished by Winlight. This is the first part of the outer corrector lens. A few words about the focal plane array. The sensor is actually composed of 4 independent CMOS, backside illuminated CMOS chips produced by Tower Jazz. Overall, we have about 100 megapixels. You see these 4 parts at the top of the diagram, and you can see the heat pipes going out and the electronics cable going out. The main properties of the focal plane array given in the table. We require, as I said, the high QE in the UV, more than 70%. The way we achieve it is by adding a high K dielectric material with a high dielectric constant coating on top of the backside illuminated chip. And this, for some reason, which I believe is not fully understood, leads to the accumulation of negative charges, and it plays the same role as implantation, like bone implantation that is being carried out by JPL. So I'll show you that we can resolve the problems due to which you need this bone implantation simply by this high K dielectric coating. And on top of that, there's a special anti-reflection coating that is intended to optimize the absorption of the UV photons to minimize the reflection. The pixel size is about 10 microns, so the overall size is about 10 by 10 centimeters. I mentioned the operation temperature, the dark current, and the read noise requirements. Unless we can go into more detail, but you'd hear much more about this from Rolf when he talks about the camera. So one of the risks that we had to overcome is to ensure that we get the high quantum efficiency that we need in UV. What you see in the right hand side is the measurement lab at DESY. You can see the Scout, which is a small piece of detector, much smaller than the 10 by 10 centimeter detector that we would finally use. Several of these Scouts were produced by Tower and sent to DESY for testing different types of anti-reflection coatings. And you see in the graphs the three different coatings. You see the quantum efficiency that was achieved, and we chose this TEAT2, but essentially they would all meet our requirements. So this risk is behind us. These plots show you on the right-hand side the out-of-band suppression that we achieve with different types of filters. These are real measurements. And we will be going with the VFV black filter that would reach us to about, get us to a few times 10⁻⁴. On the left-hand side, you see the total in-band throughput using these different filters. This includes the quantum efficiency and the optics. So the quantum efficiency was measured, the filter was measured. The optics is now a model, and it will be measured later on. And you see that we get some 30-something% total throughput. This includes the obscuration of the focal plane and everything. So about 30-something total throughput in the band in which we're interested. This is the PSF. This is, of course, a calculation. As a function of wavelength on the x-axis and on the radial distance from the center of the detector on the y-axis. And you can see that we have very good PSF in the band in which we are interested, and then it's becoming much worse as you go to longer wavelengths and also as you go away from the center. This is the average, the effective PSF on the left-hand side for a source of 20,000 Kelvin, 2 electron volts, and on the right-hand side for a main sequence G star. Let's go to the next slide. So finally, this is the limiting magnitude that we expect to achieve at different points on the detector. As I said, the optics is a model, but the coatings, the filters, and the quantum efficiencies were all measured already. And we meet our requirements of on average being better than 22.4 magnitudes with the VIV filter that I've mentioned. Okay, a word about the ground standard operations. All the data from the satellite will be continuously transmitted to the ground. We have a 5 megabit per second link. The raw data would go to an antenna at Israeli Aerospace Industries, and from there it would be transmitted directly to Waxman, to the Science Operations Center, and all the manipulations of the data would be carried out here. The Science Operations Center is responsible for all the operations that are related to the observations, to determine the schedule, the TOOs, the contamination circles if they're required, and so on. And it would be doing the data analysis, detecting the transient events on ground. Okay, we'll have all the data coming down to the ground. All the analysis will be carried out here on ground. It would generate the alerts, disseminate them to the community, and it would serve as the external interfaces to DESI, to NASA, and to LSST. I'll mention this collaboration a bit more shortly. So this is the architecture of the data center. I guess we do not need to go in much detail on this one. I do want to say a few words about follow-up observations. So we will be distributing the alerts to the entire worldwide community, but we are building our own capabilities for follow-ups here at Waxman and in collaboration with other observatories. So I would start with briefly mentioning two activities that we have for constructing follow-up instruments in Israel. The advantage of being in Israel, you can see the bottom plot here, the region marked in light blue is a region of the sky that is accessible to telescopes in Israel, but not covered by the other major facilities in the world. So being in Israel gives us a unique opportunity to observe events at earlier times possibly than other locations. So there are two big efforts in Israel, in the desert, in the Negev desert, led by Sagi Ben-Ami and Ran Ofek. One is a large array of small telescopes that will do photometry. The 48 telescopes combined could provide either a very large field of view or a narrower field of view with an effective area of 1.5 meter telescope. And the other is the spectroscopy mission. This would be a series of small telescopes connected by fibers to do spectroscopy. The effective aperture of this telescope would be about 2.5 meters, and they would have a medium spectral resolution. So both of these facilities are being constructed now, and they would play a key role in follow-up observations for ULTRASAT. And thanks to our contributions to telescopes in Chile, the SOX spectrograph for the NTT would get us some 25 observing nights per year there. And our involvement with the Magellan GCLEF spectrograph would get us about 4 nights per year at that telescope. So we'd have some independent follow-up capabilities led by the Waxman group. Okay, a word about this program management. What we've discussed so far is mainly the construction of the telescope, which is being done by DESI, Elbit, and Israeli Aerospace Industries, and the launch by NASA. All this activity is managed by the program office here at Waxman, led by Udi Netzer, who is a very senior manager from the industry with many years of experience. And in addition to this activity, we have 3 independent activities: the construction of the Science Operations Center on all the data analysis program. We have an outreach program, which I will about that. And we have a science board, which is mainly responsible for building and coordinating the work of 12 working groups working on the science of ULTRASAT, and I'll say a word about this as well in a minute. So this is a real project with real decisions being taken all the time. We have kicked off the project, meaning signed off contracts with the industries in September of 2019. The major modifications that we had to decide on are marked here in sort of light red, and I mentioned them. This is the modification to the spacecraft due to the launch to a GTO instead of GEO, and the addition of the filter. The modification of the spacecraft caused us some 6 months delay in the design, but it did not change much the time by which we will be in position in space, because a launch to GEO would require us to drift to our location for several months, and this GTO launch will get us directly with our fuel to the position that we need. So no major changes so far. This is the projected timeline. We are approaching CDR by the end of this year. The camera would be supplied by DAISY by the end of 22. Then it will be integrated into the telescope by ELOP by the end of 23. And the satellite will be constructed, integrated, and ready for launch in Q3 of 24, and the launch is planned for the end of 24. I would not talk much about the financing. I would just mention that this is it's not a cheap mission, but what we say is it's an affordable mission. It's about $110 million, including the launch for the entire mission. The main risks are the timeline. We have a very challenging timeline from kickoff to launch in 5 years. It's very fast. We have complex interfaces between the different partners of constructing the satellite. And the issue of contamination that I've mentioned is a key issue, which is that we monitor very carefully throughout the mission. We have already an outreach program being started in Israel. We believe that this science mission would have a high impact on attracting talented young students to science and technology. So I would not go into details here, but we are building some particular program for physics major in high schools that will be part of their matriculation exam, which will be related to ULTRASAT. And we are starting this year a wider scope activity of our Science Outreach Institute, the Davidson Institute, that would have ULTRASAT as its flagship project for the coming few years. I want to say a few words about the collaboration. As I mentioned, there are 12 science working groups of ULTRASAT focusing on different science topics. I've mentioned several of those: the gravitational wave follow-ups, the supernova explosions, the stellar variability in the connection of planet habitability. We have an AGN group, a TDE group, and other groups that are being constructed. And most of the Israeli astronomers are already members of these, of one or more of these groups, and are taking active participation in them. As I mentioned, NASA will be providing the launch. The science return is 8 US PIs that will be funded by NASA that would be members in the science working groups of ULTRASAT. And the project scientist of NASA was chosen to be James Rhodes, I guess you know. Our DAISY partners, their science return is 3 DAISY PIs in the working groups. And we are in advanced negotiations also with the LSST Rubin collaboration. We are planning joint Rubin ULTRASAT alerts and several additional USPIs that would get access, would become members of the ULTRASAT science working groups in return for access to real-time access to Rubin data for Israeli astronomers. And I will end with the science impact. I believe that ULTRASAT will revolutionize our ability to study transient events in the universe. Its discovery volume is 300 times bigger than GALEX and some 100 times bigger than any other observatory, which is observatory that is currently operating, and it will be operating in a unique waveband of the UV. It would provide continuous observations of these transient events for months with a minute cadence and sensitivity 22.4 magnitude. And it would send real-time alerts to the entire ground and space-based community of telescopes that would be able to follow up our newly discovered transients. I believe that it would have a broad impact on many subfields of astrophysics, as we discussed, gravitational wave sources, supernovae, variable and flaring stars, AGNs, TDEs, but also compact objects and galaxies and more. And it would provide all this with not a cheap price tag, but I would say an affordable price tag for a space mission. Okay, and I think I've...
yeah, thanks, Eli. Thanks very much for giving a comprehensive review of this imminent mission. You're just a bit over 2.5 years or less than that from launch, it appears. So it's time for questions. At the bottom of your Zoom thing, there's in reactions, they can raise the hand. And after your question is answered, please lower your hand unless you have another question. Okay, so we are open for questions. Okay, Aaron. Go ahead.
Can you hear me?
Yeah, we can hear you now.
Thanks for the great talk. Yeah, I put this in the chat. I actually have a few questions, but the first one was about what was the science driver behind going to GEO and GTO? Was it continuous stairs, or was the driver not science, and then you realized that you could do cool science with that?
No, the driver was science, and it has several advantages being in GEO. So one is being able to have an immediate continuous access to a large fraction of the sky. Being at low orbit, you have more obscuration from the Earth. Second, we want to have a continuous communication to the ground in order to have no delay between detection and announcement of the events. And another issue that was troubling for us was the oxygen 2 line in the atmosphere that is just in the middle of this waveband, which produces a very large background, also when you are at low orbit at 500 or 700 kilometers. And this is something that you don't need to deal with at the GEO orbit. So for these three reasons, we wanted to go to GEO.
Thank you. And I had another quick question, which was about the slew speed of the mission and the spacecraft. Is it set? Do you know what it is?
Yes, and we have so we have a lower limit to the slew speed, which is sort of a few degrees per second.
So will you be capable of responding to early, I guess, negative latency gravitational wave alerts on relevant timescales? Like if you have real-time commanding in 3 degrees per second, should be possible.
Yes. So as I said, yes, we should be. Yeah. Maybe not to all parts of the sky, but for
Right.
a large fraction.
Okay. Next, Wenbin.
Hi, Ellie.
I went in.
So I want to ask about the 15 arcsecond PSF. So I'm not very sure about the number density of UV sources brighter than 22 magnitude. Are they well separated such that this 15 arc minute PSF would not introduce overlap?
As I'm okay, first you have to be careful that we set this an upper limit, but our typical PSF is about 9 arcseconds, or a bit better than this in the end, so it's much better. And the second, yes, they are. I mean, we don't have too many bright sources in the UV.
I see.
It's yeah.
So this is truly just for transients. There are not so many. The most part of the sky is dark, and then they're just booming bright. The bright transients will be picked up. I see. Thanks.
Okay. Any other question? Okay, fine. Roger.
Hi, Ellie.
Hi, Roger.
I have a couple of questions that sort of go back to our early discussions of earlier ULTRASATs and the Schmidt corrector. You've got a doublet with calcium fluoride. And if I recall the image, it looks like it's got quite a high aspect ratio. I know it's a strong material, but I'm wondering how you're dealing with the launch vibrations. When we looked at calcium fluoride for the duet proposal, we actually redesigned the entire optics to avoid having a calcium fluoride corrector because it needed to, we're being forced into having such a low aspect ratio that the mass of the optics was dominated by the corrector. And you're not doing this. You've found a way out of this somehow.
I'm not sure that it is a very high aspect ratio indeed. What do you mean by a very high aspect ratio? So
it doesn't look very thick. It doesn't look very thick in relation to its diameter, but perhaps I'm unclear about which of the two elements is the calcium fluoride.
So I'll show the figure again.
Yeah, that would be good.
But your question, it is very heavy indeed.
Yeah, okay.
It is heavy. So we didn't, yeah, it is heavy.
I'm sure you've worried about it. Maybe I should ask Sagi perhaps about this question.
So you see now you see the plot?
Yeah.
So it's not very thin. These are a couple centimeters scale here.
Oh, that's very thin.
Okay. So according to our analysis, and we have already done the initial vibration analysis, we believe that this is thick enough. But if you have some reservations about this, we'll be happy to talk about it.
Yeah, I do wonder. Might be worth discussing offline. Okay, so I have one other question about.
So you think that this aspect ratio is too challenging?
Everybody I was working with was worried about something that's that thin. Now it is a meniscus, and that's helping. So perhaps the meniscus shape is effectively increasing the aspect ratio. Anyway, that's probably too much detail for this audience.
Okay, so but I'll be happy to pick it up offline and talk more about this. Yeah.
Yeah. Okay. One other question, which is a very basic one. Can you go back to your slide, which shows the relative survey speed of different telescopes? And I think it'd probably be good to emphasize the origin of the advantage of ULTRASAT.
Yes.
Do you know the one I mean? Right at the beginning of your talk.
This one, I guess.
It's coming. Yeah, that one. Okay, so here's ULTRASAT as king of the heap here, and it's as good as LSST. Now, as you know, I'm very familiar with ZTF, and I can say that ULTRASAT and ZTF have about the same N10 ULTRASAT's got 4 times the field of view of ZTF, but about a quarter of the aperture, maybe less than a quarter. Has a larger field obstruction. It has lower QE. So the one thing it's got going for it is the low background in space. So is that the entirety of the advantage? Is that where it's coming from?
So okay, for this plot, there are several things that play. One is the much lower background in the UV. The other is that this is for a fairly hot source of 2 electron volts. So
okay, so this is not just the photo detection efficiency, but actually it's taking into account the spectrum of the source.
Yes.
Okay, that's fair.
And another factor that we do take in here is the fraction of the time that you can actually observe below some air mass on the ground compared to the space.
Okay, well, it wasn't entirely clear from the slide. I didn't pick up on all of that. So thanks, that makes it much clearer.
Okay.
All right, I'll yield to someone else. I'm sure I have many more questions, but I'll let someone else ask. Thanks.
Sure.
Okay, back to Aaron.
Hi, yeah, I just wanted to follow up on this previous question about the TO time, because after your response, I recalled that on the slide you had said that the average TO time would be like 10 to 15 minutes. So I wanted to clarify that I was asking about effectively negative latency gravitational wave alerts that would be put out about 60 seconds before merger. And my point was that with the low Earth occultation and a 3-degree slew speed, it seems that you should be capable of responding to these and getting on target at the time of merger, as long as you're not dominated by your settling time. So do you know what the settling time is and whether it matters here?
The settling time is going to be very short. So it's, well, this is something I don't have an exact number for, but it would be seconds. But there would be some time also from receiving the alerts that you would be disseminating, processing it here, and getting the command up to space. This would also take some time. So 60 seconds. I will need to look at it more carefully, to give you.
Yeah, I'd be interested in understanding what your operational side delays are, because at least looking at trying to do this with SwiftBat, most of the delays are actually once the command gets to space, if you manage to do it. And since you claim to have real-time commanding, it doesn't seem like that should dominate. But I think that would be a very obviously amazing capability if ULTRASAT is able to do it and probe extremely early times where we're not only talking about kilonovae, but other things like neutron precursors or anything even earlier.
Okay, so this is a good point. I will look at the I will look at the exact numbers, and we'll get back to you, and we'll see if I think that at least for parts of the sky it should be doable. But before I say it, we need to make I need to make sure that all the numbers are small enough. So I'll check them and get back to you.
Thank you very much. This is amazing.
Eli had a couple of questions. One is, are you now truly going to be in a geo orbit, or is that a graveyard?
No, it's a real geo orbit.
So there are no restrictions on science. I thought it's very hard to get a geo slot.
Well, it is a headache. but we do get a slot at Geo. You have to show that you don't interfere with other satellites that might be there, both in terms of dynamics and in terms of communication. So this is Israel has some slots, and there are satellites that would be positioned there, and we will get an exact location and waveband, and this will be done. But it did take significant work to actually come into agreement with the other partners there. Yes.
I see. And there are some responsibilities of being in GEO that after the mission is over, do you have to do something to the satellite or just leave it there?
You have to evacuate the position and go up to a graveyard orbit, so which is about 300 kilometers. Mm-hmm. So this implies that you need to save some fuel for deorbiting, and we have this is a small amount of fuel compared to the amount that you need for circularization in the GTO. Maybe one thing that I didn't mention is that we have a reliability requirement of 3.5 years, but we would carrying a fuel that should enable us to operate for 6 years. So I hope that the mission would live at least 6 years. Then we will evacuate. Just a second, again, the lights.
What about, I saw you had a tank of helium. What is that for?
So when you use up most of the fuel in the main tanks, you need to pressurize the tank so that you don't have the sloshing of the fuel. So the helium is pushing the liquid fuel from the fuel tanks.
Okay. The last question I had is, the original ULTRASAT design, you didn't have this engine to take you from GTO to GEO.
Right.
And that's double the mass of the spacecraft. Mm-hmm. So has that slowed your sluice speed and all those things? Has that propagated into the?
No, it didn't. We managed to keep the agility of the satellite.
I see. Despite a larger moment of inertia and all that.
Yeah, we use some different wheels now. Yes.
Ah, you do. Okay. Okay. So let's say we're approaching the end of the talk. It's 9:23. We have a few more minutes. Are there any other questions? Okay, I'm not hearing any questions here. So thanks, Ellie, for giving the talk. And Ilaria, thanks again for running the club.
Thank you for joining.
Okay. Bye, everyone.